on Tangible Landscape Open Source Environment for GeoAGS and Geo4All. The GeoBite will last approximately 1 hour with a brief question and answer session at the end. This GeoBite is also being recorded and will be accessible from the ASPRS website in approximately 24 hours. Helena Mitasova is our opening presenter. Helena, go ahead.
Welcome everybody to the first webinar in the Open Source Geospatial series, which is offered collaboratively by several geospatial organizations. And you have heard some of it just explained that Geo4All is education and research outreach initiative by Open Source Geospatial Foundation, which is a non-profit foundation support of UCGIS, University Consortium for Geographic Information Science, which is a consortium of over 60 universities here in the United States who engage in research and education in geographic information science. And we are very grateful for ASPRS for providing the infrastructure to deliver this webinar. The webinar is presented from the Center for Geospatial Analytics at North Carolina State University, and it was prepared by Geo4All Laboratory. Our center is an interdisciplinary research and education facility where we engage in geospatial computing, analysis, and geovisualization. And you will see some of the examples of these activities in our presentation. We also offer professional master's degree in geospatial information science and technology, and in 2017 we plan to launch the PhD in geospatial analytics. And you are welcome to explore our website to learn more about our center. In this presentation, you will hear from several people. You already heard my name. I'm Helena Mitasova. I'm professor at the Marine, Earth and Atmospheric Sciences here at NC State, and I'm also Associate Director of Geovisualization at our center. Then you will hear from my PhD students. First, Václav Petráš will explain you how to create three-dimensional models and how to put together tangible landscape setups. Then Anna Petrashova, the lead developer of Tangible Landscape, will explain you the software, and she will also show you some cool applications. Payam Tabrizian, who is a student from College of Design, will give you an overview of some of the latest developments that involve coupling tangible landscape with immersive virtual environment. You won't hear from Brendan Harmon, who is currently traveling and he is in London at the conference, but you will see him in some of the slides, and he is the creative lead behind the Tangible Landscape. And finally, the sixth co-author is the Ross Mintenmeyer, who is the director of our center, and he provides many new ideas for interaction and applications, and he always challenges our team to new challenging developments. So why are we interested in tangible landscape interfaces? I am pretty sure that you have seen yourself in the situations that we show in the photos. We often get together around a screen to solve geospatial problems, and we use usually mouse or sometimes even touch to manipulate the data. And this can be pretty challenging, especially if the data are three-dimensional. And as the three-dimensional data are become ubiquitous because of all kinds of new technologies that can acquire them, the manipulation and working with the GIS data is becoming more challenging and requires often special training and special software. So a couple of years ago, the researchers at MIT Media Lab tried to address this issue and developed first prototypes of tangible interface for three-dimensional data. Their first prototypes were called Sandscape and Illuminating Clay, and we were fortunate to work with the developers of Illuminating Clay to explore the possibilities to couple their system with geographic information data. So with the grant from the Army Research Office, we were able to build a system here at North Carolina State University and link it with GIS. So this was the first system that actually worked with the real-world data. And the system was based on laboratory LiDAR, so it was pretty expensive, not very flexible, and that limited its applications and it limited its adoption at other places. But it still worked pretty well, and it allowed us to actually explore the concept and develop first applications. The breakthrough in tangible interfaces came with new generation of low-cost three-dimensional sensors, and specifically widely available Kinect. Several systems were developed using Kinect, and the best known among them is probably the augmented reality sandbox that was developed by Cat Caves at University of California, Davis. You might have seen this system at museums or various events where it generates a lot of excitement. We were also able to take advantage of Kinect, and for the first time we were able to couple real-world data with the real-time scanning and create a tangible landscape which allowed people real-time coupling with GIS. And you can see in this video how the system actually works. So you can modify the landscape by hand, and you can get real-time feedback on how your modification impacts the process that you are modeling. In this case, it is the water flow. So how does the system work? You can see, you have already seen the landscape model in the previous application. And with this landscape model is scanned three-dimensionally by Kinect. The data from the Kinect are input into GRASS GIS. The digital elevation model is computed, and then the data are analyzed, and a simulation is run, and the results of that simulation are projected back onto the landscape model. So in this way, Tangible Landscape couples the digital data stored in GIS with physical model that serves as an interaction device, and through continuous cycle of 3D scanning, geospatial modeling, and projection. So the first question that we get when we present this system is, how do you create three-dimensional models that are actually based on real-world GIS data? And Václav will explain you different techniques and different approaches on how to create these models.
Well, the first option is to build a model from sand using your hands. You can use projector to project contours and elevation color on the surface, and then you can build a model from sand. We are using polymeric sand or kinetic sand or moon sand. All of these names are possible. More advanced way is actually use Tangible Landscape to guide you through the process, giving you automated feedback as you are building the model. It's scanning, the Tangible Landscape, it's scanning the table and the sand on the table, computing the difference between the model on the table and the desired digital elevation model, and projecting this difference on the table. The blue color will tell you that you should add sand, and the red color will tell you that you should remove sand. You can also notice here a histogram built into the legend And at the beginning the histogram was pretty wild, but now you see that as the model is getting closer to the desired digital elevation model, the histogram, the differences are just around 0, and the histogram actually has the shape of a Gaussian curve. Together with the colors, we project also the contours to give you the general idea which model you are actually building. We found this pretty useful. A fairly precise model in a relatively short time. And here you can also see that when you need to have model for tangible landscape, all you need is actually tangible landscape itself. What you can do, of course, is to just 3D print the models. This works, but it is actually relatively expensive, and the models can be only small and they are quite fragile. A better option we are using is CNC routing. This works well for large models, and from user perspective it's very similar to the 3D printing in the way that you have your digital elevation model, you convert it into the instructions for the machine, and then you let the machine do the work. The CNC router is carving or routing using a drill from the material instead of adding, which is what the 3D printer is doing, and the material which it can carve from, it can be wood, it can be dense foam, or it can be MDF, that's medium dense fiberboard. The models created by this technique are large and are quite robust. The largest model we built was 1 meter by 1 meter. However, the models which are carved and the models which are printed, they both have the disadvantage that you can't actually change them. You can't change the surface. So what we do is that we carve a mold, and we use this mold to cast or to form the polymeric sand into the shape of the terrain, and by this we get very precise model which can be modified by hand. We are also currently experimenting with creating the models in the lab, and in the future we would like to use a small CNC router or a robotic arm to create a model from sand directly in the lab. What you can see here, it's a CNC router creating the sand model by itself. So maybe at this point you are probably excited and you want to build a tangible landscape right away, right? So how do you do that? So first you need to decide which setup you want to use. You already know that you need projector, scanner, the physical model, and the computer. You also need a stand to hold the projector and the scanner. One option is to actually have the projector in the ceiling, mounted in the ceiling, and by this you just need one small stand for the scanner. This works pretty well, but the issue is that you can't move this setup anywhere outside of your lab. With the short throw projector, you can move the setup if you put short throw projector on a short stand and you have another stand for the scanner. The disadvantage is that the short throw projector creates a lot of distortion. Then for smaller models you can use just small projectors, and this will make the setup quite portable, and you can of course go on and on with different variations of the setups. This is our favorite setup with a medium-sized projector mounted on a stand which can also hold the scanner. And finally, for a really large model, the model which is 1 meter by 1 meter, we used a special projector which we are able to mount at the same place as the scanner, very close to the model, but still project all over the whole model with really low distortion. Here is the list of hardware you need if you want to build Tangible Landscape. And the good news is that it is overall not that expensive. At the Tangible Landscape Wiki, we list all the necessary parts with suggestions for particular products. But right now, I would like just to emphasize that we are trying to keep the price as low as possible. And if you can replace one part by something better or cheaper, you can do it. And we would be happy if you let us this know, or you edit the wiki so that everybody can actually benefit. Hardware is relatively cheap, but it gets even better. You don't need to purchase any software licenses because all the software we are using is open source, but I will let Anna to tell you about that.
So let me give you a brief overview of the software behind Tangible Landscape. Tangible Landscape is built around GrassGIS platform. So as some of you probably know, GrassGIS is an open source, multi-platform and multi-purpose geographic information system which offers a variety of simple to more complex tools for geospatial analysis, but also for remote sensing, network analysis, or hydrology. So Tangible Landscape has three main components. The first one, r.in.connect, is a Grass module which communicates with Kinect. It continuously receives data from it and processes the point cloud into a digital elevation model. Then we have Tangible Landscape plugin, which is integrated into GrassGIS GUI, graphical user interface, and it serves for controlling the Tangible Landscape and controlling the scanning parameters. Finally, the third part is the Python file with geospatial analysis, and we basically these analyses are organized into functions which are called for each new scan. And what is nice here is that we developed the library with different geospatial analysis, but also you can design your own workflow using GrassGIS application programming interface. All the dependencies are open source. The main dependency is GrassGIS version 7. We use Grass for geospatial modeling and for visualization. Then the communication with Kinect is done with libfree-next2 library. And then we use PCL, point cloud library, for processing of the point clouds. So how do we control Tangible Landscape? So it has three interfaces. The Tangible User Interface is basically what Tangible Landscape is about. So we let people modify the model, interact with the GIS through the physical model. Then we have the Graphical User Interface to operate Tangible Landscape, to control scanning parameters which can differ for different models. And then finally the Application Programming Interface, where you can use Python to design your geospatial workflows, and we have some examples for that. We developed material for a workshop at FOSS4G North America this year, which you can check out. So the flexibility of Tangible Landscape is not just in the variety of geospatial workflows you can use it with, but we also develop multiple ways to interact with the physical models. So far, we have been talking mostly about using your hands to sculpt the model and to sculpt and change the continuous surface. However, some applications require different types of input data, objects, for example, like points, lines, or areas. So we developed some other interactions. In this case, we actually use wooden markers to specify point locations, which can then represent, for example, viewpoints or trailheads. Then we started also to experiment with using laser pointer to draw lines, points, or polygons on the landscape. And finally, the last one, we use a colored sand to specify polygons on the landscape. And the color of the sand specifies certain property of the polygon, and the height of the sand can represent the intensity of that property. So now I will show you some of the applications we developed with Tangible Landscape. One of our first motivations for building Tangible Landscape was to experiment with how topography drives certain processes such as erosion and deposition, and also to look in the links between topographic parameters such as slope, aspect, or landforms. Topography is also directly linked to visibility. So here we explore viewsheds. So the model represents part of our campus, and we created from a digital surface model, so it includes the canopy. And here we use the interaction where you place the marker, we identify the position, and dynamically compute the viewshed from that place. And the viewshed is then represented by the yellow color projected on the model. So in this way you can very easily, intuitively explore viewsheds in your area. So here this application is about a little bit different scale. We look at solar analysis. We try how different building configurations, what kind of solar energy and cast shadows they create. So, for example, here the animation you can see nicely the different patterns that emerge when we look at the solar energy during the year. In this application, we use a little bit unusual data type, voxel model. In GRASS terminology, we call it 3D raster. And basically, we start with three-dimensional points, measurements of soil moisture. We interpolate it into a 3D raster, and then we explore this data set using Tangible Landscape. So by digging into the sand with your hands, you can look under the ground as if you were standing at an excavation site. And what happens is that we compute a cross-section of the scan surface and the 3D raster and project it back on the model. And the colors there then represent the soil moisture at the particular place and depth. We can also extend this concept by combining with different interaction. So here we use the markers to draw the line which represents a profile, and then you can look at the profile here. In this example, we couple Tangible Landscape with a more complex simulation, a wildfire spread simulation. So first, we just let the fire spread without any intervention on the model. So our model again is built based on digital surface model, so it includes canopy. So now what we do is we remove part of the canopy as we would be creating a fire break. So we rescan the model, we identify the fire break and change the initial conditions of the simulation. And now you can see the model, the fire spreads, but it stops at the fire break. But here, due to spotting effect, it jumps and continues spreading. Here we look again at a completely different scale. regional scale. We couple tangible landscape with urban growth simulation, which called Futures, which was developed here at the center and is implemented in GRASS GIS. So by placing color sand, the participants are designing different zones. The red zone is for, it attracts new development, while the green zone is for conservation. And now we again rescan the model, identify these zones, and change the initial conditions for the model. So now you can see the growth of the city during the next couple of years based on the new initial conditions. So recently there has been a lot of excitement about serious games and how we can use them to engage people in science, into science. So we thought that using tangible landscape would be a great idea for this. So we developed a couple of serious games. One of them is a coastal flooding game, where people are trying to protect homes on the coast during a storm surge when the fortune is breached and floods the homes. So they were trying to build the different coastal defenses, different barriers from sand, and then they could see how effective they were. And through this process they learned a lot, mainly that when the breach comes, the houses can be flooded even if they are far away from that breach. Another one is about termite infestation, where people were trying to manage the spread of termites across a city by treating city blocks. So they were placing the wooden blocks which represent the treatment, and they were trying to look for a configuration which would most efficiently stop the spread of the termites. Why we call it serious game is that we were actually running in the background a biological invasion model implemented in R. And now I will let Payam show you some of the current work we have been doing.
So as you have seen so far, tangible landscape represent the landscape as a projection of augmented model, which is perceived as a bird's eye perspective. We couple tangible landscape with an immersive virtual environment so that human scale views can be rendered on devices like head-mounted displays. This allowed us to integrate the ecological analysis with human perception measures such as aesthetic evaluation and landscape preferences. So how the extension works, we just need to add 2 additional components to the tangible landscape setup: a 3D modeling software and a virtual reality headset, which then can be replicated in a display. So for 3D modeling, we use Blender, a free and open source program for modeling, rendering, simulation, animation, and game design. Blender has internal Python-based IDE and add-ons for importing GIS data. Also, it has add-ons for integrating immersive virtual environment headsets such as Oculus DK1, DK2, and CB, the new consumer version. Briefly describing the automation process, GRASS GIS and Blender are loosely coupled through a file-based communication. So as user manipulates the tangible model, GRASS sends a copy of the geo-coordinate information or simulation to a specified system directory, where Blender constantly monitors the directory to update the 3D model. In this way, user can simultaneously interact with large-scale landscape models and its 3D clone that represent human-scale fine-grained elements such as trees, water bodies, roads, and buildings. So for demonstration of how the system works, we prepared a small video where Anna and Wotflav are collaboratively designing a landscape. Thank you. So Wotflav starts by sculpting the topography to create retention ponds, which is mainly to address what stormwater management requires of the site. As he carves the landscape, Water flow and accumulation simulations are continuously projected onto a physical model. In the same time, point cloud and water polygons are transferred to update the tangible model and the 3D Blender model. Then he collaboratively works with Anna, as you will see soon, to place the excavated soil on site to create artificial mounds, which are mainly to provide overviews to the site and aesthetic qualities. For showing human scale views, we normally took benefit of the laser pointer interaction. You can delineate the desired viewpoint and orientation on the landscape, which is processed as a line feature as sent to Blender and update the camera location and orientation. User can explore the landscape with the mouse or with the immersive virtual reality headset. Also, polygon features can be delineated with laser pointer and can be defined as patches of trees, for instance, to populate predefined diversity and density of vegetation. In this demonstration, you can see only one type of tree is used. However, the Blender script can be adjusted to take various types of plant species. Shading, textures can also be included to add to the realism of the scene. In terms of trail design, you can also use tangible objects. So tangible objects can be also processed in the application. For instance, here, wooden cubes represent checkpoints that denote recreational trail. GrassGIS simulates the optimal route using algorithm that simulates a least cost path walking. But Václav wants to complement the trail experience and adjust it to pass through the new forested patches. So you can see the line feature not only represent play, but also process in Blender as a walkthrough simulation, which you will see in a second. You can explore it with a mouse, or you can put on the virtual reality headset. I will now pass it to Helena to wrap up.
So maybe now you are asking, so where do you use it? What kind of settings, what kind of users, user groups would be interested in this kind of environment? So one of the first and a very natural group of users are designers, and that's what actually the tangible landscape was originally intended for. So for landscape designers, it creates a collaborative, very intuitive environment with real-time feedback on what the impact of their designs would be on different landscape processes. So, and our College of Design has used tangible landscape already in their courses, and they are now installing their own system so that they can use it both in research and in education. In terms of education, we have been using tangible landscape in our GIS courses at the graduate student level, where we use the system to explain surface analysis algorithms. It's great, for example, to explain not only the water flow that you have seen, but also such relatively abstract concepts such as curvature. You can explain the landforms very well. So it works quite well at college level. But it is very popular also among the kids. We brought the tangible landscape to various events, open houses, where kids can interact with it. Of course, for them it's very natural to play in the sand, and they are very excited when they see, when they do some changes in the sand, that also the image that is being projected changes. Sometimes they don't quite understand what they are seeing, but for example, water is pretty intuitive, and they use all kinds of very creative ways how to change the landscape. We also have projects where we explore tangible landscape as a platform to support decision making and to communicate science to public and decision makers. And you have seen, and Anna has already described the the serious game. So that's one approach, how to engage public and create the environment where they can learn a little bit more how the processes spread throughout the landscapes. But we also use it we are also exploring it as an environment where decision makers can actually collaborate in trying to find better solutions to some persistent problems. So the second example is actually exploring the control measures for spread of sudden oak death disease. And we also found, as we were working on tangible landscape, that it is a great tool for research and development. It allowed us to improve and extend many modeling and analysis tools in GRASS GIS. So GRASS GIS users have benefited probably quite a bit. And we also found that it's great for testing new algorithms and tools, because you can generate different landscape configurations in a very controlled way, and then you can test your algorithm whether how robust it is, how reliable it is, and whether it can handle certain specific situations. So in this example, Vašek was developing a tool for visualization of gradients of landform migrations, for example, dunes. So he created several snapshots of this dune migration and then used that as an input for developing and testing his module of this visualization, dynamic visualization of gradients of landform migration. So as we already mentioned, all of the software that is associated with the system is open source, and we share it on GitHub. So here you can see the link to the GitHub repository where the Tangible Landscape plugin can be downloaded. Also the GrassGIS module for importing the data from Kinect is available, and again you can use it for different applications, not only Tangible Landscape. We have also set up Tangible Landscape repository on Open Science Framework to handle this as a open science project, so you can access it there as well. And finally, we provide several resources for those who are interested to learn more about Tangible Landscape. We have a Tangible Landscape website. You can see the link here. And here we post all the latest, newest developments that we do to encourage collaborative development and sharing of different setups and results and applications. We have set up Tangible Landscape Wiki. So if you are considering designing your own Tangible Landscape, please share with us your setup and your applications here on Wiki. And finally, last year we have published book, Tangible Modeling with Open Source GIS, which is published by Springer. And there is a link on these slides to that book. And in this book you will find the GRASS workflows for the different applications that we have developed for Tangible Landscape. You have seen some of them already in the when Anna was showing these applications. And you can also find there in appendix various applications that the students in our courses have developed for Tangible Landscape. So this is all that I have, and thank you very much for your attention, and we will be very happy to answer your questions.
Thank you. We do have a few questions already on the question box, so let's start. First question, is there a special type of sand to be used in this process?
Yes, as Vašek has mentioned, we are using so-called kinetic sand, and it's broadly available in toy stores and in Brookstone, and online we buy through Amazon. So whoever has small kids they usually know what this kinetic sand is. It also sells as what it is called moon sand and other types. It has about 2% or something like that of polymer, and that polymer holds it together. So you can have a very detailed, very precise shape using this sand. And it made a huge difference for us because with the first version of Tangible Landscape we used plasticine, which was much more difficult to work with. So that was another breakthrough. What I would call breakthrough in using the system is the kinetic sand.
Okay. Next question. Roughly, what's the total cost of a system setup like the one that you demonstrated?
Yes, you could see it on one of the slides. It's between 2,500 and 3,000, and that includes the laptop or the computer. So if you already have a computer with high-end graphics card, then it's much lower. And there is a slide that actually shows the example system. But as we mentioned, you can, here it is. You can adjust that system to whatever you want. You can use more expensive projector, or you can use different kind of stands, for example. But the Kinect itself is very cheap.
Good. Next question. Can you be specific about the version of Kinetic to use? In the slides, I've seen Xbox One, and in another one mentioned Kinetic version 2. Which one is the one that you recommend?
The application now runs with the version 2. We started,
okay.
I think this picture here used the first version, but now we moved to the second one. So this was an older picture, but now we use the version 2. I don't know if it's called Xbox because they changed. It was Kinect for Windows, but basically version 2 is the latest one. That's the one we use.
Have you used or considering QGIS instead of GRASS? Will QGIS work with any of your examples?
Yes, we have definitely considered that, and we are actually looking into the option right now as well. But to process the data from Kinect and to do the subsequent geospatial processing, we actually need the algorithms which are in GRASS. So even in QGIS, we would be actually using GrassGIS through QGIS processing or through QGIS GRASS plugin. So it's definitely an open option, but also there is a strong reason why we choose GRASS, and that's because of all the analysis which is there available for us, for the processing itself, and then for the algorithms we want to build on.
There are many sophisticated modules in GRASS for dynamic processes and things like that that we are using and that are readily available, that allows us to connect to the tangible landscape smoothly. Mm-hmm.
What can be used as a substitute for the sand?
For the sand, as I mentioned, I have the kinetic sand is really the best so far, and there are different types of it. We have used previously plasticine. Again, that's something that you can find in toy stores. And we also use, as we mentioned, for some of the application, the just carved models, and then you don't change the surface, you just add objects to it. So, and you know, it's open, there are new materials popping up anywhere, so I encourage people to explore different materials. But the kinetic sand so far has been the best.
Next question. I'm assuming I wanted a model for a target area, let's say 21 by 25 kilometers. What size model will be ideal?
Yeah, so the size of the model is limited by the Kinect resolution. So essentially the largest model that we did was 1 meter times 1 meter, but you also need to think about what kind of features you want to modify. So it's really like this basic cartographic task that you need to do to identify the size of features, identify the size of the model, and how big those features will be. Because I found that sometimes we just move a sand a little bit, but it may be hundreds of thousands of cubic meters of sand. So one really has to do some computation in terms of the scale. You can use larger models, but then the Kinect resolution will be lower, and then you can't really do such fine features. So it doesn't scan at the resolution so that you get the fine features. So there is a lot of flexibility, but you need to consider the resolution of your data and the resolution of the things that you want to explore and modify.
And also, you have to consider how much money you want to put in the projector. Because if you have larger models, then the projector, for example, on this slide is pretty expensive because of the special lens, which allows it to display large picture on a small distance. So we generally it's more convenient to work with medium-sized or small models than with the large. Then it becomes a little bit hassle also because of the equipment.
Okay, I have a question, but it's two questions into it. How much of this work will be moved away from the physical modeling and representation of landscapes to VR models in the next 5 years?
Do you understand the question?
I'll repeat it.
Can you tell the question again?
Yeah. How much of this work will be moved away from the physical modeling and representations of landscapes to VR models in the next 5 years?
So you are thinking that we would move from the physical model to virtual reality? Is that what you are asking? So actually with this 3D modeling, we are trying to get out of virtual reality and the real 3D tangible world. And we couple it with virtual reality. So you get both because in virtual reality you can't really touch it, feel it, you can't feel the shape very well because you are always going through the mental process of transforming the virtual reality to the actual three-dimensional shape. So that was the whole idea, is really to stay in the physical three-dimensional space, but we are coupling it with the virtual reality so that you can then step into that landscape at a human scale and see it in the virtual reality. So we believe that it will be both.
And the second part of that same question, what are the merits of the physical models versus the virtual models?
Yeah, they are much easier to modify. And we already, Brendan, who is not here, he has done some experiments with people. For example, he just gave them an example, like create this landscape topography, very simple landscape topography. And he gave them the task, create it in a computer software. He used Rhino and another one. And then he had them to create it with sand. And they were much more successful in creating that three-dimensional geometry in sand by hands than in the software. And it was even for people who were very experienced with the software, because the software has lots of limitations about what kind of geometry it allows you to do. And you can do it very precisely, but it takes a lot of time because you have to define lots of points that you need to move. And also the software, the way how the computers are moving the surfaces, it's not how the natural processes are moving and evolving landscapes. So there is a big difference. And we also have seen that when you are working in a virtual environment, you are alone. You are not really naturally interacting with other people. So that's why this is another advantage, that when we bring people here and they are working on the tangible landscape, on the 3D model, they can see each other face to face and they immediately start talking to each other. While in the virtual environment, you are, even if you can communicate with our people, you are pretty much alone.
Last question. Oh no, we got another one. Will be there a Linux version?
There is already.
Okay. And the last question, how is tangible landscape related to participatory 3D modeling?
Oh, it is essentially participatory 3D modeling. So it just provides one option how people can do participatory 3D modeling. And I think it's an excellent option because, as I said, it allows people to participate in the 3D modeling and decision-making using three-dimensional data without learning the three-dimensional software.
And the difference here that it's augmented with the geospatial analysis. So you can, if you do the change, you get immediate feedback about what your change affected in the studied phenomena. So it's not static. And maybe if I can talk about the Linux version. So it's running, currently we run it on Linux and Mac. We don't run it on Windows. It's theoretically possible if you manage to compile it, but we haven't done that, so we recommend Mac and Linux, specifically Ubuntu.
And that's our last question. So I want to thank everyone for excellent presentation. And I also want to remind everyone that our last GeoBite for the year is September 9th. Feel free to register. Thank you, everyone.
Thank you very much for having us. Thank you.